Hello there chemistry fans, this is an AQA A-level chemistry video and it's looking at carbon-13 NMR. So the previous video looked at the introduction to NMR, so if you haven't seen that you should watch that one first. And this one's going to focus on carbon NMR being simpler than proton NMR, and we're going to look at how we can use the data booklet to identify some structures of molecules given the spectra. First up though, if you don't subscribe, please do. Your support is very much appreciated. Thank you. Okay, so let's just get rid of this one first because you haven't seen any carbon NMR or you haven't seen any proton NMR. So I'm going to show you some. Let's have a look. This is what a proton NMR looks like. And this is an example of a carbon-13 NMR. Now, to the untrained eye, they might look quite similar. However, if you look at the bottom one is quite simply just 5 peaks. That's all it is. It's 5 peaks. If you look at the bottom one, I'll count them for you just in case you can't count. 1, 2, 3, 4, 5 peaks. Yes, we've got chemical shift along the bottom. Notice how the scale goes down. It goes from large chemical shift to small chemical shift. That's always the case. So it's quite unusual that the x-axis decreases from left to right. Anyway, back on track. So to the untrained eye, it might look like the proton NMR only has peaks in it as well. So you might be forgiven for thinking 1, 2, 3, 4 peaks. However, there's definitely more information on that proton NMR. They are definitely more complicated. Look at these numbers. So a proton NMR, we get something called integral values. And now, for those maths fans, integral, or the integration of a line or a graph, it's the area underneath, and that's kind of what this is. It's the area underneath each peak. So each peak has an area or a peak area. We call it the integral value. More of that on proton NMR, but the carbon NMR does not have that. The proton NMR does have integral values. The carbon-13 does not. Furthermore, there's my GCSE English for you. The proton peaks can be split. You can see that they look like, they've got split ends. They need to go out themselves a nice good conditioner like I use. So peaks can be split in a proton NMR. Now I can see that's actually split into 4. My eyesight's probably better than yours, but that's been split into 4. As has the one to the right, that's split into 4. The third peak looks like it's split into 2. And the fourth peak looks like it's split into 3. Now they don't all have to be split, but they can be split. You will not see splitting patterns in the carbon-13. So I think we can draw a conclusion here that carbon-13 NMR are much simpler than proton. Carbon are literally just give you peaks at a chemical shift. Proton doesn't. All right then, so let's kind of have a look at this chemical shift. We are given a data book. Use it. Okay, you will see that table C, so don't get your table B and table C mixed up. Table A, in case you're wondering, is infrared spectroscopy. That gives you your wave numbers for each bond or different bond environment. That's a different topic though, isn't it? So table C is the carbon-13. Don't get them mixed up. Right then, so what we're going to do, we're going to look at our data book, table C, and I've got this NMR. Now what we have to remember, if we were proper scientists, we'd have access to other bits of kit as well, and we'd be able to run this sample through a machine that's going to give us the percentage composition. And from the percentage composition, we could work out an empirical formula. And then what we could do is we could find out the molecular mass using mass spectrometry. And then from the molecular mass and the empirical formula, we could work out the molecular formula. There we go. I found the molecular formula. So I know that this substance has 5 carbons, 9 hydrogens, an oxygen, and a chlorine. So what we're going to do is going to go through each peak in turn. I'm going to go from left to right. So I'm going to start on this peak here. And I'm going to look at my data book. So this is around about 195. Looks like it's just under, so let's just be fussy and call it 194. Now, if we look down this list, The only thing that appears around about 195, the only thing it can be is this down the bottom here. That's all it can be. So this has to be a carbon double bonded to an oxygen in an aldehyde or ketone. So we know that this has to be an aldehyde or a ketone. Can't be an ester or an acid. Now it can't be an ester or an acid anyway because it only has one oxygen in it. And I've now accounted for that one oxygen. I've also accounted for one of the carbons. So I'm kind of playing bingo here. Right, let's move down to the next peak. The next peak is around about 53 or something. Looks about that, doesn't it? It's below 55. Yeah, let's just call it 53. So chemical shift is 53 ppm. Right, what could that be? Well, it couldn't be this one. So it can't be the first one. Could be the second one, possible. So it could possibly be this one. It can't be the next one because that's 20 to 50, so it can't be that one. 25 to 60, it could be that, but then again, it actually can't because there's no nitrogen. So actually, no, can't be this one. Can't be that. 50 to 90, possible. Actually, no, it can't because it can't be an alcohol because I've got no oxygens left. It can't be an ester or an ether because I know it's not already. I eliminated the ester or ether from the first one. So actually, it has to be a carbon next to a halogen. That kind of makes sense as well, actually, because it's going to be a carbon next to a chlorine. So this is going to be a carbon bonded to a chlorine. So I've now accounted for two carbons, my oxygen and my chlorine. Right, next peak. What's this one? This is around about 25, 30, just below 35. So yeah, 30 something, call it 35. Around about 35. Now, it can't be this anymore because we've already accounted for our halogen. So it can't be that one. We also know that that's not in there. So it can't be that one. And all of these rested too high. So either has to be this one or this one. One or the other. It kind of makes sense that we need a carbon next to a carbonyl because we've got a carbonyl here, look. So I know that there's got to be a carbon bonded to this. Got to be. Okay. I then also have two other carbons here. What's this one? Carbon, this is around about 20, just above 20 actually, is it? Hard to tell. This is 25. So yeah, it looks like it's just above 20. That's quite significant, I guess, because that could then be another carbon on the other side of this carbonyl. And then finally, my fifth carbon is all the way down at the beginning. So that's just your average run-of-the-mill alkyl carbon. So it's just any old carbon. So what I need to do really is kind of stick this molecule together because I've not finished it. Kind of, there we go. So I've got bits. I've got like, not quite fragments, I've got bits of this molecule. So let's try and build this molecule. We've got a carbonyl bonded to a carbon. We've got a carbon this side. We know that there's a carbon. That would work actually, wouldn't it? Does that fit my structure? Let's play bingo. 3, 4, 5, 6, 7, 8, 9 hydrogens, 1 oxygen, 1 chlorine, and 5 carbons. Yeah, I'm going to suggest that that is a possible structure for that NMR, given that molecular formula. Okay, so let's try a slightly different task then. So here I've got 4 different carbon-13s NMR. The top left has 3 different environments. The top right has 2 different environments. The bottom left has 2 different environments. And the bottom right has 3 different environments. So one of these 4 spectras is in fact propanone. Now, if we look at the carbons, remember this is a carbon NMR, so we're interested in, we're going to focus on the carbons. The carbons on the left and the right, so both carbons in the CH3, would be classed as being in identical environments. The carbon on the right, the carbon on the left are in identical environments and therefore only cause one peak. The carbon in the middle on the carbonyl is slightly different, it's in a different environment, so that therefore this would have two peaks. So propanone has two environments or two carbon environments, so it either has to be top right or bottom left. So now we're going to have to use chemical shift to decide which one it is. Now because this is a ketone, I can go straight down to the bottom and expect to see a peak between 190 and 220. That's using my data book. So there should be a peak between 190 and 220. So that means that it has to be this one. Okay, next up we have propanoic acid. Now this has three carbons. Don't just assume that means three peaks, because we have to check if there's any symmetry or identical environments. And in this case, all three carbons are in different environments. So this would be three peaks. So this is either top left or bottom right. Now, using the data book and the chemical shift, the carbon in the acid, so the carbon in the C double bond OH, should be around about 160 to 185. So that means it has to be bottom right. Next up, we have pentane. Now, pentane definitely has some symmetry here. So although it has 5 carbons, the 2 carbons either end are in identical environment. Then the 2 carbons, so the 2 CH2 groups, so if I look at this carbon and this carbon, they are identical, as are these 2 carbons. They are identical. And then this carbon in the middle is in a different environment. So we'd expect 3 peaks for this molecule. And all of them would appear between 5 and 40. So this is in fact the top left. And last up, we've got 2,3-dimethyl-but-2-ene. Now again, this has many carbons. It's got 6 carbon atoms. That doesn't mean 6 environments. We've got to check. So all 4 of these are actually in identical environment. They're all exactly the same as each other. So they would all cause 1 peak. These 2 carbons are also identical. They would cause the same, so just 1 peak between those 2. So we'd only expect to see 2 peaks. And if we look at the data book, a carbon in a double bond you would expect to see between 90 and 150. So that's this peak here. And the peak over on the right is due to the other 4 carbons. Let's have a look at some exam questions. How many peaks in the carbon-13 NMR of 1,4-dimethylbenzene? Right, well, let's draw benzene. 1, 2, 3, 4. So there's 1,4-dimethyl. And we're looking at carbons. There's lots and lots and lots of symmetry going on here. This carbon and this carbon are identical. So there's 1. This carbon here and this carbon here are also identical. 2. And then actually this and this are the same. And they're actually the same as these. So there's only 3 different environments here. My answer is C, 3. Question 2. Slightly different because it appears to be symmetrical. However, there's not any symmetry at all here. So all carbons are going to be different. So it's tempting at first glance to think that this and this are the same. But they're not, look. If you're thinking that there's a line of symmetry there, there's definitely not. Look at this side of the molecule. It's absolutely not symmetrical. So this actually has all different environments. 1, 2, 3, 4, 5, 6, 7, 8. They are all different. None of those carbons are equivalent or in the same environment. Okay, one last question then. So looks complicated because there's a lot of writing here. Draw one possible structure for each. So compounds F and G have the molecular formula C6H4N2O4 and both are dinitrobenzenes, right? What do we mean by dinitrobenzene? Well, benzene looks like this. Dinitro means that there are two NO2 groups. So this would be an example of dinitrobenzene. When you think about it, actually, there aren't many possible scenarios we've got, I suppose. There's 1, 2, there's 1, 3, or there's 1, 4. There's only actually 3 possible structures for this. Right, let's see if we can count the carbons. 1, they'd be equivalent, they'd be equivalent, and they'd be equivalent. This would only have 3 peaks. I'm saying that's G. Let's go bottom right now. 1, 2, those number 2s would be the same. 1, 2, 3, and 4. I think there's 4 peaks in that one. And then this one here, 1 and 1. Ah, yes, this has only got 2 peaks. So this is F. There we go. Practice, practice, practice. That brings this video to a close. NMR is all about repetition and practice. You've got to keep practice as many questions as you can get done. Good luck.